Very welcome, everybody. How are you doing? Hope everybody is having a great day so far. Getting closer to the end of the week, and of course, we are gonna have a study break next week. So it's gonna be a good time to relax a little bit. Today, I'm going to open up a new discussion, which is going to be interfacing. Very important and beneficial topic in embedded system application. So far, we've learned embedded system is a system which has both software and hardware. And in the hardware part, we have both input and output. Over the last couple of weeks, we've practiced using some input, such as what? In order to have some analog input to the system, we use keypad, we use some switches. These are some of the examples in order to become familiar with interfacing. We started officially interfacing, but I haven't touched the point or I haven't touched the keyword interfacing so far. We already practiced how to use keypad in order to send some signal to the system and of course interact with some of the output. So I want you to come up with some of the examples, since I believe everybody at this point is confident to introduce some of the existing input and output in our embedded system platform, or I would say set up inside the lab. Any idea? What do we have as an input into the system? Any example of our inputs? Okay, we do have some keypads, we do have switches. What else? We do have multiple input, analog inputs, such as even potentiometer, such as joystick. But the one that we are using for interfacing is only the switches and the keypad. Switches and keypad, as you can also see here on my screen, they are going to be some of the devices that they can send input signal, and then we are going to display them using LCD or LED. Either of them also can be considered as some interfacing devices for embedded system. We do have LCD, we do have LED. Of course, we do have many different output devices in our setup, but the one that we are focused on learning about them as an interfacing is just LCD, LED, keypad, switch. There are many more, such as, for example, in other application, or I would say in other examples, such as even barcode reader, or even a smart card acceptor. Remember, sometimes you just scan your card. Those smart card acceptors, all of those are going to be considered as an interfacing within an embedded system. So this is going to be what we are going to learn. And of course, later today, while I'm explaining about interfacing more, I'm going to introduce what methods are available to us as an engineer in order to have, anyway, we are going to receive some input signal. But not always those input signals are in the perfect situation. Sometimes they do have some noises. Therefore, we have to learn how to filter out those noises. So far, because of the PWM, or I would say even in mechatronic course, I taught you about some filtering circuit. And of course, we touched the terms pull-up resistor, pull-down resistor. So these are now known. Now I'm more confident when I'm talking about this stuff. The words are not unknown. You really had a great experience practicing those skills. So now I'm going to just a little bit go advanced. Filter circuit also is something known for you, because last 2 weeks I opened up the first order low pass filter circuits for PWM application. Therefore, at least you have an understanding of filter circuit. Most of the time in electrical engineering, when we are designing filter circuit, we are focused on a circuit including capacitors and resistors, which are two simple components but very beneficial in electrical engineering, and we can use them for many different applications. Today, we are going to learn about another brand new filter circuit, but this time for debouncer circuit. We call it debouncer circuit. Still, we are going to call it filter circuit or RC circuit, but a different application of RC circuit, not the one that it was a low pass filter circuit. Therefore, the location or the position of the capacitor and the resistor can really be important in defining which kind of filter circuit we are designing as engineers. So far, you know what the summary for the conversation is about. Like interfacing means looking at the input output, how to just filter out the input signal in a way that we are going to have a good understanding. And definitely from there, we are going to learn about designing those filter circuits. So let me this time, before I forget, share my screen. Then you are going to see what I'm doing. Okay, so now you have that understanding in terms of the big picture where we are standing. This is the learning outcome. I already explained it. Right now, we are focusing on the interfacing method, which is going to be, again, designing the filter circuit. We are having only one extra topic under the embedded system. Also, input-output or CAN interfacing is another method, or I would say another version of advanced interfacing method. CAN communication is another interfacing method. Still, through CAN, we are going to control the signals, and somehow we are going to have a better communication between the software and hardware, but this time through CAN. Therefore, either you are using keypad, switch, and then looking at the output through some LCD, LED, or whatever, or you are using CAN communication. Both of them are considered under interfacing for embedded system. So later we will open up another CAN communication discussion after you are back from the study break. And then we are done with the embedded system. We will move to the, as you can see right in here, we will move to the automotive electric, means a little mechanical will be involved in the next half of the semester. Not only computer application or embedded system or programming, we are going to also learn about like the mechanical part of automotive. So let me start with the structure of a actually switch, and of course why we need to learn about pull up, pull down. Again, I know that I already introduced it, but in case somebody forget about it, I'll touch it again, I'll open it up again, and we'll go from there. What you can see in here is the mechanical switch. This is what we call it, a mechanical switch. Mechanical switch definitely means we are going to have some spring being involved or being connected. Today, if I show you the actual switch right in here to the arm of the switch, there is an arm for the switch, and there is some spring connected to the arm, and that's why we call it a mechanical switch. So now, what you can see right in here is going to be a single pole, single throw. Why I call it single pole, single throw? Do we have any other type of switch? Definitely, yes. And what's the definition? Single pole, single throw means in this kind of switch, I'm going to have only the switch to be connected to one input, and of course, be able to communicate only to one output. There are situations we do have more poles and more throws. Even you may see it right now in here in the room if you check on the walls, or you may see it in other applications. So we have double pole, double throw, or so on. Therefore, all I want you to at this point learn about like the structure of the switch, the number of the pole and the number of the throw is going to consider for you or define for you how many inputs or how many outputs you have, right? So that's why we call a switch. Like, for example, in here in this picture, a single pole, single throw is going to receive, it's going to be connected to one input, and it will be connected to one output only, not multiple outputs. In addition to that, more specifically in embedded system, and any situation that we are going to communicate with something like a microcontroller, which is an advanced device, an updated, advanced, modern even device, we call it, we are going to have some pull-up or pull-down resistor. Actually, pull-up resistors are some fixed value. I'll call them right in here. These are fixed value resistor. Means you are not expected to change the value of the resistor. They are not something like a potentiometer that you can adjust it and you can change the size of it. It's fixed. And most of the application, they are going to be built-in pull-up or pull-down resistor connected to the input of that setup. For example, I'm focusing more on the one that we have in the lab, the setup that we have in the lab. Remember, our switches, the 8 switches, toggle switches, are connected to port T of the microcontroller, right? If those are connected to the port T of microcontroller, if you can recall from that schematic, the big schematic of the setup in the lab, which I continuously show it to you during the lab time, I already show you on the side where you have those switches. On the left side of those switches, you have this pull-up resistor. In the previous lab, I asked you to also activate them. So most of the time, this is super important to understand, you are not going to have an external pull-up resistor or external pull-down resistor to the system. Those are already there. They exist right in there. All you want to do as an engineer, you have to command them to activate them, right? Those are sitting for you to activate them if needed. So I'm going to just one more time remind everybody about the structure of the pull-up and pull-down and what's the difference between them. If I'm going to simplify the difference between pull-up and pull-down, in terms of a structure, both of them are just the exact same resistor and capacitor. Of course, you do have some pin of the microcontroller to be involved, and you do have ground and voltage source to be involved. Like, for example, a pull-up resistor is a type of resistor which is going to, suppose this is your voltage source, I call it voltage source, and this voltage source could be either VCC or VDD, right? Based on the application, but I'm going to be general. I'm going to say voltage source. And then if you have your resistor, your fixed resistor to be connected directly to the voltage source, I'm going to call it, if it is directly, I'm going to call it pull-up. And then pull-up resistor means when the voltage is connected directly to the source, it's going to control the flow of voltage between the voltage source and the pin of the microcontroller, and this is your microcontroller. And of course, on the other end, you are going to have always a switch, and then it is grounded right in here. I'm going to call this one maybe R1, and I'm going to call this one C1, switch S1. R1, S1. These are my pull-up resistor. So now, if you are going to have, what will happen if you do not have a pull-up resistor? If you do not have a pull-up resistor, you are going to have a short circuit. That's very important. If you do not have this one, you're going to have a short circuit. That's why we are going to add a pull-up resistor with a fixed value in order to control the connection of the voltage supply and a certain pin in, like this is going to be like a digital pin. This one is a digital pin of the microcontroller, not the entire microcontroller. This resistor is not connected to everything. It's just connected to one digital pin. For us, if it is the switches, it is going to be the digital pin for the port T. And then we are going to have, in the other hand, pull down resistor. Suppose again you do have VS, the difference between pull up and pull down. Now switch is connected to voltage source. Instead of being connected to ground, now I'm having like the switch to be S1 is going to be directly connected to the voltage source. And then I'm going to look at the voltage between, now microcontroller is still here, but if this one is open, I'm going to get rid of the voltage source. Therefore, the pull down resistor means a resistor connected to the ground. And still, I'm going to call this one R1. So now look at the system. This is a pull down resistor. And in here, resistor is connected to ground, but in here, resistor is connected to the voltage source. That's the difference between them. So if you need a low default impedance state and you want to pull the signal to high, then you need to use pull up. And otherwise, And if you need a pull down resistor to pull the signal, if you want to pull the signal to low, then you need a pull down resistor. Make sense? That's the difference between these two. Now, we already had the discussion of how to find the resistor, or how to find the resistance. What is the right resistance if you are going to be an engineer designing it? But in the concept of this course, you do not need to design that one. That's already inside the setup. All you have to do, you have to use a command through the port T, which is usually PERT, assigned to like activating it. I already have it right in here for you. I'll show it to you. You have to just activate it in order to just use it in the system. So now, knowing that one more time, pull-up resistor is going to help you to control current flow from the voltage source to microcontroller, and pull down is helping you to control it from microcontroller to ground. That's the difference between pull-up and pull-down. Now, I'm going to give you one example in case, like in the lab, that you are going to activate it. You already had it, but one more time. For us, it is port T. It is connected to port T. Definitely, I have to just enable port T pull-up resistor. And I have a command for it, which is PERT. And activating it means what? Turning it to input or output. Input is the switch. I'm going to activate it. So I'm going to make it FF. And that's how I enable port T pull-up resistor. We had it in the previous codes as well. So having that in mind, now you have that understanding of the pull-up. And I also mentioned this one right inside the slide. You can see it right in here. Most of the time, we are going to have pull-up resistors. Thank you. We are going to have pull-up resistor to have a like limit for the current. And that one, for example, the resistor should be something in between this range 1K to 10K, 1 kilo ohm to 10 kilo ohm, in order to look at like the application for the interfacing. Any questions so far? Next, let's look at the structure of the actual switch. This might be interesting for many of you to learn. I'm going to maximize this slide. Probably none of you, or at least most of you, never know that when you push a toggle, push a maybe switch or toggle a switch, the contact between that input and output is not going to happen immediately. Most of the time, based on the quality of that switch, there are lots of bouncing. As long as you push that one, you are done with the pushing, but the bouncing is happening inside the contact. Look at here, this is the structure of a regular switch. And in here, you do have two contacts. These are, in fact, some conductive material. And since these are conductive material, after they touch each other, it will create an arc, right? Because they are conductive material. And after they do have that certain arc, then definitely you are going to have like some signal to be generated based on that arc, right? So, but the most important part of it is this contact will generate arc, and arc will transfer the current through this contact. So that arc will generate your current and it will be transferred. And then what will happen? These are not going to connect and stay connected. These are going to open and close, open and close. And most of the time that opening and closing may happen in 5 to 10 milliseconds, and even the number may be up to 100. 5 to 100 times within the period of 5 to 10 milliseconds. See how many bouncing that may happen in there. And after that, as a result, we are going to have such a signal, because this is going to generate 1 and 0, means low and high, means it is connecting, it is disconnecting, and each connect is a high, each disconnect is a low. Therefore, we are going to have in 5 to 10 milliseconds, hundreds of these 1 and highs. And that's a factor of the quality of this contact, the number of that bouncing. Therefore, if we are going to have such an input to the system, it's not going to be something effective, especially when we are using microcontroller. It may cause some damage for our electronic devices. And then as an engineer, we have to think about it, how we can remedy the situation. I'm going to have such a high and low turn on and off signals to the system. Therefore, we are having some method in order to fix this situation. We have two types. One type is going to be fixing, or let's say designing a system which we can fix the situation through software. Through software means we can command the microcontroller using a delay or interrupt. And now you are familiar with what delay is when I'm talking about the delay, or what interrupt is when I'm talking about the interrupt. Therefore, software means we can use a command inside the C programming. For us, we are using C in the lab, and then delay or interrupt will help us to just a little bit fix the situation. But I don't think this is gonna be really efficient. Why is that? Because when I'm applying delay or interrupt to the system, means I'm going to keep the microcontroller busy for a longer time, which simply means I'm going to waste a lot of time and energy. And of course, if you are going to use the same computer for different applications, it will impact the other applications on that computer, like functionality of other application or softwares on that computer as well. Therefore, also this is a method that can help in situation like, for example, for a student project or for any situation that we are limited with a budget to go purchase a better device, then sure, you can use the command through programming in order to filter out the signal and get rid of this, like I would say jumps, because there are jumps between on and off. So this method is possible. I'm going to show you one piece of code as an example on how we command the microcontroller to do this for us. But there is another method like hardware. Remember at the beginning of the class, I told you today we are going to learn about designing another type of filter circuit, which we call it debouncer. Still, it is RC, means resistors and capacitors. We are going to look at like the size of resistance, the size of capacitance, but at this point, it's a little bit different with what we learned last week about low pass filter circuit, right? So to run RC debouncer circuit, we are going to just filter out these jumps, these highs and lows, and somehow get rid of the noise causing this. Anyway, remember, this is a somehow combination of electrical, mechanical. Switch is a mechanical, right? Is a mechanical device. If these two contacts in here, they are going to constantly for some time, for a period of time, just touch each other, it may even generate some noise. How about that? That's another thing that we have to think about it, how we can control it. Therefore, while we are designing a RC debouncer circuit, which in the upcoming slide, I'm going to draw it for you. What does it mean when I say a debouncer circuit? We have to consider another device, which we call it Schmitt trigger, in order to filter out the noise generated by contact, right? Therefore, that's another difference between this debouncer circuit and that low pass filter circuit that we learned about last week. So before that, let me quickly start with software debouncing, and then I'll try to just finish up for today right in here, because we are going to have the quiz as well. I mean, the assignment as well. So I'm going to finish it with software debouncing, and then next week when you are back, I'm going to teach like any component about hardware. I'm going to teach you how you can calculate your proper resistor, your proper capacitor in order to design your debouncer circuit. So look at this piece of code. Most of the time, such as software debouncing, we call them wait and see method. Simply means, again, as I said earlier, we are going to use delay or we are going to use interrupt. Delay and interrupt always means wait, or stop for some time and then start again. That's why we call it wait and see method. So again, we are going to have like maybe some bouncing for a duration of 20 to 100 milliseconds. And we are trying to filter out those high and lows and generate something closer to, let me show you, something closer to this filtered signal. But the thing is, through software, we can never get this close. But still it will happen, definitely. It will be, so this is without the filter. This is the signal without the filter. We are trying to use some filter in order to just smooth out these jumps. Through the software, we cannot smooth it this much, but still it will be better than not having a filter. So first method in here is going to add some, for example, interrupts or some delay, either of them, into your system. In here, I'm going to delay 1 millisecond. In here, when I'm like defining in here to start counting from 0 to 20, simply means go ahead, every 1 millisecond, give me a signal up to 20 milliseconds. I'm going to finish it up at 20 milliseconds. So I'm going to collect almost like 20 signals, either high or low. I'm asking, give me delay 1 millisecond, means every 1 millisecond, generate a signal based on the situation of the switch. If it is high, high. If it is low. And why I say based on the situation? Because it is debouncing. It is bouncing. Each time it is bouncing, I press it one time. I do not continuously on and off. I press it one time, but the on and off is happening inside. So therefore, after that, this is going to, in here, let's say, consider I'm receiving 20 signal. Every 1 millisecond for example, 20, I'm going to receive 20 signal in here. And then I'm going to, and you can continue this one up to even 100, up to whatever, based on the application. And that's why I say this is not efficient, because it's going to generate lots of like input output for you, which is going to be not efficient, is going to keep the microcontroller. But there is one benefit in here. This one can control or can filter out multiple switches at the same time. And if it is going to control multiple switches at the same time, it will continuously generate some information, keeping the computer busy. So this will continue until the switch is completely off, or until somehow we are disconnecting it. That's why I say also it might help in situation that you are limited with budget for that small project as a student, but it's not efficient. It's not something that big companies for manufacturing or build project, they can use it. It's gonna be really non-accurate, and it will waste a lot of time, a lot of energy. So I'm gonna stop this lecture right in here. Next time when you are back, I'm going to introduce designing your RC debouncer circuits. I'm going to solve for you some example to make sure you can, as an engineer, design your circuit when needed.